We have seen the maximum contiguous subsequence problem solved by two different approaches already. Both of them search the whole spaces and try to find the best answer, which is the maximum value of the sum. Then we want to see if we can further remove one more loop, which means that we only use one loop. Can we still solve the problem and make it become a linear algorithm? In our previous algorithm, we have two loops, one I loop and one J loop. I want you to make a guess. I loop indicating where does it start, J loop indicating where does it end, to depict the range of the items they want to sum up. So if I want to remove one more loop, make a guess. Are we going to remove the I loop or are we going to remove the J loop? Surprisingly, the answer is we are going to remove the I loop actually, and we will be able to solve the problem using the linear algorithm, which means we only have one single J loop to walk through the whole array and find the answer that we want. So let's take a look at this. This is actually pretty tricky. It uses a very smart observation to step quickly over a large number of subsequences that cannot be the best, which means that we only look for the possible solutions, and there's quite a few combinations of the sequence are not necessarily to be investigated. Let's take a look at this. How do we do that? The maximum contiguous subsequence will not, start with a negative value. So take a look at the examples that we have been using. The first element is a -2. As a human, we would know that that's something that we don't want to be included into our answer. So that what we need to see is that, we can basically find the answers without including the very first item because it's a negative value, and we found our maximum sum over here. While we we continue to look into the next item, we are getting a fewer positive value, but still a positive value. However, when we walk through over here, the sum of the whole thing become a negative value, which tells us that we can treat the whole thing from 0 to 6, all of these items as negative items, just what we see before. So we know that if the answers relies on the next part of the array, all of these are negative values already, and we want to get rid of those because they cannot be part of our answer. And therefore, you can see the descriptions over here. We will not start with a negative value or a combination of numbers that gives a negative value. In other words, all of these considered as a negative value, they cannot be part of what we are going to search next. So take a look at this one. The algorithm keeps only the J loop to go through every item. The I is not a loop anymore. I will indicating where do we start. It will always start with the very first location. And J will start with the same location as well. While J moving, indicating the combination of the start and the end of the locations that we want to look into. When we see a negative value, then we move our I to the next location because that cannot be part of what we are going to search next, because it will not give positive value. It will only decrease the value, so it cannot get a maximum sum that we are expecting to do. While we keep going through all the positions, J will keep moving until we see that the sum of that range become a negative value. Then we move. So you see that it's not letting use I to walk through all the items. We move it from 1 to 7 directly. And that is how we will be able to remove the I loop. Let's take a look of the algorithm and follow by an example. So you can see that in the algorithm, it's mostly very similar to the previous code. We try to finding out what is the size of the array, and then this is somewhere different. You see that we initiate this sum equal to 0, make sum equal to 0, right before we go into any loop. So this sum has been moved to the outside of the loop because we only need one this sum value and we only need one maximum sum value. We then initiated I as 0, indicating that that is the starting point of the I, and then we only use one loop. So you can see that this is the only loop that we're using. For j greater equal to 0, j less than nj plus plus. Then here is the key. This sum will sums up where j looking at. If this sum is greater than the maximum sum, we try to remember all of this information, just like we did before. Here is the special thing. If this sum is less than 0, as we mentioned earlier, we would make I goes to the next location, which equals to j plus 1, and then we reset this sum, because that means we cannot get the that cannot be part of the answer. So we have a fresh start. I will go to a new location, the next location, and have a new start because it's a new start. So we reset this sum equal to 0. Let's take a look of the example and then be able to understand it correctly. The same thing, I'm going to put the code on the left side and then try to trace the code of it. So you can see that the same example that we have initiated n equal to size, which is 10. We initiated maximum sum equal to 0, this sum equal to 0, I equal to 0. So again, I is not a loop anymore. J is a loop. It will start with 0 location. So this is the very first beginning of the J value. This sum equals to 0, which is this sum plus -2 because J is at this location. And then we have a -2 over here, so it will equals to -2. Because this is a negative value, so that it will, obviously it's not greater than maximum sum because the maximum sum right now is 0. It will trigger this else if statement, so I will equal to j plus 1, so I will move to the next location, and then we reset this sum because we don't want this sum to become -2. And then when I move to the next location, j will also move to the next location because j is a loop. Then we will continue the operation. So I is 1, j is 1. This sum equals to 4 because this is a 4. And then since this sum is greater than maximum sum, we try to remember the value. Okay. Now I will stay at the same location because the sum is greater than 0, it will not hit this part. Now we will move our j to the next location. So in the loop, j will move to the next location. At this time, this sum equal to 4 plus -3, where j is looking at, and then equals to 1. Now 1 is not greater than maximum sum, and 1 is also not less than 0. So nothing happened. We will just keep moving j to the next location. So while j moves to the next location, this sum will continue adding the next value. 1 plus 2 equal to 3. It's not greater than the maximum sum. It's not less than 0. Nothing happened. So j will keep moving to the next location. So when j moving to the next location, this sum equal to 3 plus 7 equals to 10. So now 10 is greater than current maximum sum. So we want to remember the value of it. And next, j will move to the next location, and you will see that this sum will keep adding adding the -4 equal to 6. 6 is not greater than maximum sum. 6 is not less than 0. Nothing happened. Now something special happened. When j move to the next location, this sum will keep adding that, give us a negative value, just like we see. Since this sum is less than 0, we need to initiate a new start. So I will move to the next location of the j. So I equal to j plus 1. And this time we reset this sum value so that we have a fresh start. And therefore, we will move to the next one. Maximum sum still stays what we have found before. This sum is 0. I equal to 7, j equal to 7. This sum equals to 5. Not happening anything, not hitting any if statements. So the next thing, j will move, and therefore we will add one more value, which is 9. 9 is not greater than current maximum sum, which is 10, so nothing will happen. It's still positive. And then we will move our j to the next location, and this time we add a negative 1 over here, get the value of 8, and that basically is it. You can see that the j start looping from the beginning to the end, and then when it goes through everything, that's the end of the program. That is the big O of nlinear operation. In order to make sure you understand it, I want you guys to have an assignment. And this assignment is something very similar to the previous assignment. Given the array looks like this way, I made a little bit modification on the values over here. And then I also injected 3 cout, 3 outputs of the operations. The assignment is similar to the previous one. I want you guys to apply this program on this array and then tell me what is the exact output of the program. And once you are able to go through that, you should be able to understand fully about this linear operation. So, to sum up, if it's possible, write a code to test your algorithm for various large of n to really understand how is your program going to perform. Big O is an estimation tool for algorithm analysis. It ignores the cost of many different things. It just gives a rough estimation. Sometimes n log n versus big O of n operation. While we take a big O notation, we know n is actually smaller than n log n. Sometimes this kind of operation has some big overhead to initiate it. So it depends on your n value. We know linear is faster than n log n. However, if the input data size is very, very small, then it is possible in reality linear algorithm runs slower. So that's why we say testing different things is a very important practice. Here is the most important slide on all. For nested loops, if the loops are nested to each other, the total time is affected by the product of the loop size. Remember that when we're looking into the n-cube operation, we have one cube nested with another cube nested with another cube. That's why, and each one of them is running on according to n, which is the input data size. So it's n multiply n gives you an n-cube operation. So if they are nested to each other, they are the cost of the time is going to be a product of the loop. However, if they are running as consecutive loop, in other words, if I have another loop over here saying that after all of these operations is done, so this is a consecutive loop that you can understand. So this loop will not do anything with here. It will wait until everything is done, which is n cube, and then with another loop over here will run n time. It will become a n cube plus n operation. So in this case, you can see that this will give you a loop as a consecutive loop, and the cost is going to be considered as the sum of that. To write the big O notation, ignore all the constant value, ignore the plus sign and everything, only provide the most dominant term. And this time, you see this practice before, at this time, you should have a better understanding of what the meaning of the big O notations, as well as what is the program will looks like in terms of these operations. So that would conclude the big O analysis lecture And in our next lecture, we will look into lists.